Bismillahirrahmanirrahim wa bihi nasta'in. This lecture is about assembly line or assembly line balancing. This really a great problem in manufacturing systems is to balance the assembly line, because if you divided the tasks of any assembly or any work to a number of stations, if the work in one station is longer than the work in other stations, people in that long work time station will be bored and angry and try to move to other station, or try to find something to make them equal to other people. While people in the shortest or the shorter time stations, when they are free, they are going to annoy other people. And this is actually a great problem in manufacturing. At the same time, if you calculate the total time of production is equal to number of stations multiplied by the longest station time. And that means if you reduce the longest station time, you are going to reduce the time of production. Let's start our lecture. Actually, this lecture, I copied a lot of slides from other places, and they are not mine. And so I put this note that most of the contents of this lecture is copied from other people's work, so as to keep to other people their rights. It's a line balancing problem. Before I start talking about line balancing, I want to say something, that this is the greatest problem in production, is to balance the stations of work. And there are many ways people try it, and here in this lecture I'm going to talk about some approaches, but the greatest problem, those approaches are for a small number of stations and tasks. If the tasks start to increase, and say in assembly of cars, for example, where thousands of parts to be assembled, this is going definitely to make it very difficult to balance the line. So they divide it into substations or clusters, and then from those clusters they build the complete system. So as each cluster can work discretely, then they combine those in a final assembly line, right? Also, if it is not chrono time, this lecture will be taught into two complete lectures and not one lecture. But I'm going to combine. I'm going to continue talking about the whole line balancing in one lecture. It's not a lecture, of course. It is two lectures, but I'm going to talk it in one film, right? Is to arrange this line balancing, is to arrange individuals processing and assembly tasks at the workstations so that the total time required at this station is approximately the same. And this is actually what I said is the problem. We try to combine tasks in stations so as the total time of each station is approximately the same as other stations. As I said here, nearly impossible to reach perfect balance. Definitely you can't reach perfect balance, but they try to be as near as possible to the perfect balance of stations. Some terminologies minimum work element. Are going to talk about those terminologies in this lecture. Minimum work element, total work content, workstation process time, cycle time, precedence constraints, balance delay. Actually, those 6 terminologies we are going to talk about during this lecture, and let us save time and talk about them at one at each slide. First one is minimum work element, dividing the gap into tasks of rational and small size. In other words, it divides the gap into small tasks. For example, as I said here, drill a hole can't be divided. Although you are going to adjust the drill, you are going to feed the drill down, you are going to move the drill up, and you can divide it in many tasks. But here, in assembly line or in any work station line, the drill is one. Drilling a hole is one activity. This is a minimum work element as and a sample of it time for element j is equal tej, and tej of course should be a constant because the minimum work time for any element is a constant for that element. Okay, try to remember tej because we are going to use it later, and time for an element j, this is the name of the element, and so on. Let us move to the next definition. Total work content. Total work content, which is TWC, is equal to the sum between j is equal 1 and n number of elements in that component, and you are going to add all TEJ together, and it's the sum of TEJ for all the components of the work is the total work content. I think that's a very simple definition. Minimum, sorry, I think I've come back, so let's go forward. Workstation process time. Workstation process time is the amount of time for an individual workstation after individual tasks have been combined into station. That means you add all the tasks, the sum of task time of that station together to have the workstation process time. And as you see here, sum of task time is equal to sum of workstation time. And that means you add all the tasks times together to get workstation process time. And this number is more important because in balancing we try to have the workstation process time is nearly equal for all stations. Cycle time. It is time between paths coming off the line. In other words, the time of all the assembly being done on of all the assembly. Ideally, the production rate, but may need to be adjusted for efficiency and downtime. Of course, we can't say cycle time is the production rate because production rate you have to add to it the efficiency of the machines and downtime because no machines or no line can work without defects or downtime. So this cycle time. But ideally, if there is no any loss in time, cycle time should be the production rate. And of course, we need cycle time to calculate with it the maximum production rate of the system established by the bottleneck station, that is station with largest time. Of course, cycle time is the number of stations multiplied by the largest station time. And this is what he said here, established by the bottleneck station, that is station with largest time, i.e. You multiply the largest time of the largest time of the station largest with the largest time by the number of stations, right? Precedence constraints generally determined by the required order of operations. In other words, you can't do an operation unless you do another operation. Say, if you are assembling something inside the box, you can't cover the box before you put things inside it. So this is precedence. The precedence putting things inside the box, then to cover the box, and this was called precedence constraints. And usually, as you are going to see later in this lecture, we draw a kind of precedence diagram for products. As he said, draw a network style for understanding. In other words, you can draw a diagram for products as we are going to do later. Cannot violate these, and elements must be complete before the next one is started. Of course, as I said, you can't cover the box until you put things inside it. So this is the precedence, which comes first and which should come after. And if you didn't do the first task, you can't do the next task. This is what we mean by precedence constraints. Assembly line balancing. Assembly line is a production line where material moves continuously through a series of workstations where assembly work is performed. This is very clear. Station time. Let Ti time of performance task I, where I is 1, 2, 3 till n number of all tasks. Sk station j time, where Sk is the sum of Ti, the elements being done in that station, and Sk definitely should be less or equal to the maximum time, which is C, maximum station time, which is C. Definitely this is what in the green box is an obvious thing. And Ij, where task I is assigned to station J, and this is very clear also. So station time is a sum of the time of all the tasks being performed in that station, and legally this station time is equal the maximum the largest station time, or less than the largest station time, but not more than it. Performance measure. Let K be number of workstations. 1 less or equal K less or equal N, and this is also an obvious thing. Never K will be less than 1, and never K will be larger than the number of tasks being done in that station. Dj is equal C minus Sj. This is the delay time, where C is the maximum time for largest time for the large time for the station, or the station with last time is C, and the time for that station that you are working on is Si, and the difference will show the delay. And by the way, delay or I determine station J is very important for us, because if it is large, that means the station is not working for a long time. Total idle time, which is IT, is the sum of between k and j is equal 1 of dj. In other words, the sum of k between k and j is equal 1 of c minus sj, which is equal k c minus sum of course, we just changed the equation, and the line efficiency is equal to the sum between k and j is equal 1 of sk over kc multiplied by 100. Line smoothness index, and this is very important, which is si, is equal the square root of the sum of k between k and j is equal 1 of s max minus sk. S max, of course, is c minus sk square, and this will show the smooth index. And if this smooth index is equal, it will be usually more than 0, but if it is 0, that means the stations are perfectly balanced, right? And this also can be done for each station to find the smooth index of each station. And usually we try to have the smooth index of the station as low as possible, right? Minimizing idle time, minimize sample time per unit. This is obvious, of course. Minimum IT is equal to Kc minus the sum of Ti between I is equal 0 and n. If we go down to the next station, if IT is equal 0, then K is greater or equal to the sum of Ti between n and I is equal 1 over C. Or in other words, K is less or equal to n. And if you go down, T max is less or equal to C is less or equal to minimum of sum of between I is the sum of Ti between n and I is equal 1, with I equal n and I is equal 1, or m over p. Here precedence is required. But this young person with green trousers and yellow hair, he says this looks like it's MP hard to me. Don't worry about those equations, although they are right equations, but the application of them is not that much, right? So don't worry about them. Precedence relationship. Precedence constraints. Some tasks may have to be completed in a particular sequence. Means task I will move before task J and so on. Zoning restriction or zoning restrictions. Some tasks cannot be performed at the same workstation. That in this station I need a power tool which is in another station, so I have to do all the power work on that station, say welding for example or soldering. So why I put in this station extra soldering machine, and in that station also soldering machine, so I move them in one station. Some tasks may be required to be performed at the same workstation, which is called divorces. دي ذات وينس divorces طلاق يعني بالعربي، والتحت marriage اللي هي زواج. يعني in other words we try to zone work. If I have got in my tasks some work can be done by a specific tool. Don't put part of it in this station and part of it in that station, or tasks in this station and tasks in that station, and you multiply the number of tools by the number of that tasks being done in all the stations, but try to put them in the same station at the same time. If in other words, tasks cannot be performed in the same station, say because in that station we have heating element or so, and here you are going to dispense, say, a liquid glue or something like that, and it will affect it, so you put it in another station, and this is what called zoning restrictions. Example 1. Let us try to have examples, but I'm not interested in those examples. Just I want you to have the flavor of how the problem of line balancing is done. Of course, as I said, line balancing, usually if it is a small line, you can balance it by try and error or heuristic method. But if it is large one, you need tools and computers sometimes. Let us have this example. You see, here I have got 5 stations, S1, S2, S3, S4, S5, all of them are tasked. Here is equal 5. Say C is equal to the maximum time, which is in station 3, which is 10 minutes. P, you have to add all those time together and find the number of paths which are going to go out of this line, and of course the maximum is 10, and you have 5 stations, so you are going to have 6 paths per hour. The sum of Ti is equal to 36, and if you go to the green box performance measure, IT 5 into 10 minus 36, which is 14 minutes, LE 36 over 50, which is 75, and SI is 7.35. Right? Let us do something about this example. If we add tasks 1 and 2 together, find the story that it to change. Now I have got only 5 stations. K is equal 4, of course. C now is increased to 12. Production is 5 per hour. And performance measure IT, of course, now it is 12 instead of 10. LE is 75 and SI 7.48. Let us try another try. Now I have got only 3 stations, and now K is 3, C is 14 minutes, P is 4.286 per hour, and you find in the green box underneath IT is 6 minutes, SI is 4.47 and LE is 85.7. And if you have now 2 stations, you find K is equal to 2 stations, C is 22 minutes, P is 2.72 per hour, and you find in the box underneath IT is 8 minutes, LE is 81.8 and SI is 8. Now all of them in one station. Of course, SI here is 0, and which is ideal, definitely ideal. And IT is also 0, which is ideal. And now the efficiency is 100%. Definitely no loss of time. Let us have a summation of this. Of course, if I'm have to select, I'm going to select number 3, where I have got 3 stations. Sorry, 1, 2, 3. If you see K is equal to 3 stations. C time is 14 minutes. And LE is 85.7%, which is very high, and SI is 4.47. Of course, the ideal one is to have them all in one station, but that is sometimes is impossible, right? And this is a solution of example 1, and Samaniya is very happy that by your summary and your work, and he may select 3 stations as shown in this example. Let us have another thing. Example 2 of assembly line balancing. Now I've got 12 tasks, and each task, as you see, I've got the time of it underneath, maybe minutes, maybe seconds, as you wish. Task 1 is 5 minutes, 2, 3 minutes, task 3, 4 minutes, and so on. Until task 12 is 7 minutes. And here is a precedence diagram or precedence relationship. And as I said, usually in all this work, we use a precedence diagram or precedence relationship, which is similar to what we use in PERT or CPM, but got differences because the node is the operation. If you look, you can't do operation 6 until you finish from operation 1, 2, 3, 4, and 5. Then you do operation 6. But after operation 1, you can do operation 2 and operation 4 simultaneously. And you can't do operation 3 until you finish operation 4. Operation 2, sorry. And you can't do operation 5 until you finish operation 4, and so on. And this actually is the precedence. It's very important because if you want to divide work into stations, you have to put operations which are going to be done sequentially. Now let us have a trial and error approach. Here is a very simple approach. As I said, I'm not interested in all those things, but here he's trying to do something. He said find minimum number of stations for given cycle time, repeat for various cycle time, and select solutions that minimize idle time. This is the 3 steps he's going to do. And he started by summing all the time, which is 50, which is 2 stations multiplied by 5 multiplied by 5, which is 50 for all the time. If you go back to the idle, you find all the tasks, if you add it together, is 50. 5, there is 5 plus 3 plus 4 plus 3 plus 6 plus will be 50. So he used here 50 as cycle time. And if you look underneath to the green box, of course, if the cycle time is 50, which is 1, of course, here he used prime factors, and his prime factors is 2. 50 is prime factor is 2 multiplied by 5 multiplied by 5. And here, of course, the minimum stations, if you took 1 station, and it is feasible, of course, to do it in 1 station. And if it took cycle time 25 and it's 2 stations, if you look at the diagram, you can divide it into 2 stations. If you took cycle times 10 and you look at the diagram, you can do it in 5 stations, because here, as you see, the integer numbers is 2 into 5, which is 10, 5 into 5 is 25, and of course 1 is feasible in all the times. So I'm going to use minimum k or minimum station 1, 2, 5, and multiply 5 by 2 is 10, and multiply 5 by 5 is 25. Okay, and but when he multiply 5 by 2, he find he can't have cycle time of 5 minutes. So he say feasibility is 0, and he can't have 25 station, so the feasibility is 0, and the T max, of course, is equal to 7, right? Of course, he's using integer, k always integer, k always integer, okay? Of course, you can't have a station, you have to have a full station, isn't it? Anyhow, try and error approach solution. Now, he divided in another way. As a present diagram, he put rectangles around it, and he tried to cumulative sum of times. You see station 1, task 1, and time is 5. Of course, the time you can go back and find times, of course. And column sum is 5, and cumulative sum is 5. When he moved to station 2, which is got task 2 and 4, he add time of task 2 and 4 in column sum, which is 6, and the cumulative is 6 plus 5 is 11. If you go to station 3, by the way, the trial and error approach is a better approach than the other approach which we just discussed now, right? If you go to station 3, which is task which contents are tasks 3 and 5, which time is 4 and 6. The sum of them is 10, and 11 plus 10 is 21, and so on until he finds the other, finds all the stations. First, and he would do that for all the stations, station 1, 2, 3, 4, 5, 6, and 7. All the 7 stations, as he did, is like that. Okay, and you find at the end of the day the cumulative time is 50. Of course, this is not the cycle time, but it's the cumulative time of the product. Let us go to the next step. This is a heuristic method. Place each task for as far as left as possible, no restrictions to move within the column. Can move task further to the right, assign task to workstation such that the sum of the time does not exceed C, which is the maximum time of station. Always select task with longest time when forming a workstation. This is just actually procedure you follow when you use this heuristic method. You see now, he tried to move task 2 from station 2 to station 1, and task 5 from station 3 to station 2, and task 6 from station, of course, 4, which is going when you move task 6 to station 3, there will be no station 4. And now you find the situation started to change. The column sum of station 1 is 8, station 2 is 9, station 3 is 9, station 4, the new 4 is 7 because the old 4 been removed, and station 5 is 10, and station 6 is 7. And now you see the maximum time, or the cycle time of the product is 10, and the minimum time for the station we were is station 6, which is 7 minutes. And now it's a bit balanced. But if you move to another situation like this, now he fixed station 1 and 2 and 3 as we said before, and then he moved station 4, the new 4, to station 5, and from station 5 to station 4, and so on. So he changed the situation wherein now if you look at the table underneath the green table, you find station 4 got activities 7 and 8 now. Station 5 got activities 10 and 11, and station 6 got activities 9 and 12, and this will reduce that numbers, which if you go back you find 10 in station 5 now being 8, and that means the maximum C now is the maximum time for a station which is equal C is 9, and the minimum is 8. And if you look at the square on your right hand, you find now the efficiency is improved to 92.6%, which is very high. And now this heuristic method being established, being accomplished a good result for us, right? Now, another thing, what's called position weight. If you go back, this heuristic method is by try and error, but it got some, as we say here, those 5 points which you have to follow when you are doing this rectangular work, moving to another and so on until you finish by a result. And if you continue on doing that, you may have a better result if that is possible, especially if the tasks are a very large number. Now, position weight, and I think position weight is the best method for balancing the lines, and I want you to use it for the solving of the tutorial and the assignment given in this lecture. Find position weight for each task. We are going to talk about position weight where you go to the precedence diagram and you add all the tasks which come after the task. Rank task based upon position weight, the highest first. After you do the position weight, which we are going to I'll show you in moments how to do it, and then you rank them. Assign tasks to station with highest rank first. Continue to assign tasks as long as time remains. Task does not violate precedence relationship. Station time does not exceed cycle time. Then you continue to assign tasks from the table, of course, and it's very easy. Just you add until you have a time which does not exceed the cycle time. We are going to do it now. Repeat until all tasks are assigned, and you repeat this thing until all tasks are assigned, and that is it. Each task is assigned to the first feasible station, and also you could create the algorithm. Each task you have to assign it to the first feasible station. Of course, if you use a position weight, you are going to keep the precedence of your line, right? And position weight, by the way, can be done by a computer. You can have a very simple, small computer program which do for you position weight. If you have got many tasks, you can put them in this program, and you have divide them into stations. Right. Now, let us position weight, he said, is the time of the longest path from beginning of task I through the remainder network. In other words, if I want to find the position weight of task 1, you have to add 3 plus 4 or 3 plus 6. Of course, I'm going to get the largest, which is 3 plus 6, which is 9, then plus 5, 9 plus 5, and then I go on one of the two passes. Of course, the pass from 6 to 12 through 9 is not okay, so I can get the pass from 6 to 7 to 8 to 12, which is 5 plus 2 plus 6 is 11 plus 7 is 18, or you can go through the pass 5 plus 4 plus 4, which is of course this is longer, 5 plus 4 plus 4, which is longer, where you add 5 to 8, which is 13, 13 plus 7, which is 20. Okay, and now I use all of this as a position weight for all paths. If you look at, say, path number 12, number 12 is the last path, so it will be only 7. If you say path 11, you add 4 plus 7 only. If you say path 9 is 1 plus 7 only. If you say path 6 is 5 plus 2 plus 6, which is 13 plus 7, which is 20. Because if you go to the other side, 5 plus 4 plus 4 plus 7, it will give you less than 20. It will give you 5 plus 4 is 9, 9 plus 4. It is the same, of course, here. It just happened to be the same. It's the 20 in this direction and 20 in this direction. But sometimes it may differ, okay? And this is the way you find the position weight. Now, if you calculate the position weight, you find for task 1 is 34, task 2 is 27. By the way, the position weight of part 1 is the largest time of the project, okay? And so on. So now after I calculate the position weight, and this is a very important thing to how to calculate the position weight. And if you start from the end to the start, you find 12 is 7, 11 is 4, 4 plus 7, which is 11, 8, which is 6 plus 7, which is 13, and so on. And you go down this way and this way. 9 is 1 plus 7, which is 8, and you start going from right to left. You can calculate the position weight of the project. Right. Now, rank them, put the rank 1, 2, 3, and up to 12. The tasks now, you find the first task. If you look at the green box bottom left, you find task 1 is came on rank 1, but task 4 came in rank 2, and task 3 came in rank, task 2 came in rank 3, and so on. You just arrange them in that way. Okay, let us move. Now, after I rank them, I start to divide them to stations. That's very simple thing. Just have, say, station, I want to divide them into 6 stations. And if I calculate, if I go to the previous station, I set time, the complete time is of course 50. And if I'm going to say divide them in 6 stations, I'm going to do something around 10. And I put this number 10 in my mind and I start. Station 1, time 5 and 3 is equal 8. But if I add 3 again, that will increase the number to 11. So I put task number 1 and 4 in station 1. I'll go to station 2, where if I put task number 2 is 3, task number 5 is 6, which is 9. But if I added task number 3, I find it more than 10. So I'm going to say in station 2, I'm going to have task 2 and 5. Station 3, task number 3 is 4, and task number 6 is 5, which is 9. Task number station 5, I take on it task number 7, and task number 10, which is 2 plus 4, which is 6. If I took task number 8 with them, that will be 12, and I said that I don't want to exceed 10. So I move, I spare task number 8 to station 5. In station 5, now task number 8 is 6, and task number 11 is 4, which is 10, and this is the maximum thing and acceptable for me. And now station 6 is task number 9, task number 12 is 1 plus 7 is equal 8. And if you look at the last column, which shows use the sum of course should be 50, and that's it. So C now, which is maximum station time is 10. The efficiency now is 83.3, and that is acceptable. And the position weight, by the way, is the best way to use. Right? And please try to use it in your work. Right. Now, the tutorial work. As I said, those are 2 lectures, and I supposed to do them in class, but now it happened like that. So I'm not going to solve the tutorial with you. but try to solve it. And here is our tutorial. And he said in a simple line shown in the below table there are 12 activities. It's required to divide these activities between 3 stations. As you look at the table, the activities, task which he tried to describe the task, and then he talked about immediate predecessor, and please from this immediate predecessor draw the precedence diagram. We draw the precedence diagram from this immediate predecessor, and the last column is time in seconds, and you find the total time is 110. Of course, if you can't solve it, just contact me and we can discuss how to solve it together, right? And now after you finish the tutorial, please try to solve this assignment. And it looks like that one without description, but now it is 15 activities instead of 12 activities, and here you want to divide them in 5 stations, and you do the work by yourself. I think I finished this lecture and I'm going to stop here, and please contact me. In the last lecture I'm going to leave for you my email, and you can contact me on my telephone number or email if you wish, or if you need help. Thank you very much. And this is the end of this lecture. Thank you for your attention. Alhamdulillah. And see you on my last lecture, and which will be also recorded like this one. Thank you very much.